Howdy, our senior design project is to create a 3D printing head for Dr. Ty's research. This 3D printing head will utilize UV light to cure resin shape within a vat. So if you imagine the Death Star lasers, we're going to be doing a similar thing where we converge a point beneath the surface of the vat. Hydrostatic 3D printing is a unique method for SLA because it reduces the need for support structures. Traditional SLA uses UV light to cure and solidify on the surface of a resin, whereas we'll be curing beneath the surface.
So yeah, some of the problems with traditional SLA printed structures are you were required to print the product layer by layer. And so this hydrostatic 3D printing, in contrast, have three-dimensional degrees of freedom in the print. Additionally, traditional SLA structures, you are required to have support structures, but 3D or hydrostatic 3D printing uses the hydrostatic forces to support the structure. So no support structures are required. So this is really great when printing low stiffness biomedical materials that have an increased risk of damage when the support structures are removed from the product.
Dr. Ty's research group has actually already created 3D structures within resin vats with a single focus light that they have used with several different focusing lenses to converge to a single point. However, they're not very pleased with the accuracy of the shapes that they're able to create. So they would like us to create a system that uses multiple light beams to converge to a single point. And the idea is that the individual light beams will not have enough power to initiate curing anywhere outside of the focusing point. So now that the curing is occurring exclusively at this focus point, which we intend to be within 1 millimeter, we can simply move the 3D printing head to essentially draw out a path of that point, much like a 3D printing pen would.
So we will accomplish this design by breaking down to 3 sub-assemblies: the optics, mounting, and light control. For the optical components, we will be using fiber optic cables. They will be able to take one cable and send a light source through that, and then split it into 7 individual cables. At the end, a collimator will reconverge that light into a single column, and then a focusing lens will direct that light into the vat, into finally our final focus point. We will choose and implement our optical components and verify them using ZMax, which is an optical CAD software which will help verify our beam diameter and focal point.
For the mounting, we're gonna have a light extending aluminum chandelier, and also attached to that, we're gonna have optical housing units that are gonna contain our fiber optics, our collimating lenses, and our focusing lenses. And in connect with that, we're gonna have a housing connected with a chandelier or the ball socket joint to allow us to have a rotational freedom. And for the light control, we're gonna have a light that will blink on and off to ensure curing doesn't occur on the surface of the vat.
To conclude, by early November, the team will deliver to Dr. Ty a working 3D printing prototype head that will be able to attach to the existing machine in his lab here on campus. At this point, it should be as simple as plugging in an existing light source that Dr. Ty has to the fiber optic splitter, finally adjusting the individual housings on the ball and socket joints to create that focal point, and then letting the printer run. We're expecting that the final system will successfully cure the photoresin at any point in the vat, and we'll be able to begin developing whole parts in a seamless manner. Thanks for your time. Thanks, and Gigum.